This lesson will focus on simplifying, adding, subtracting, and multiplying radicals. So for our first example, we'll simplify the square root of 27. Whenever we're simplifying square roots, it helps to make a list of perfect squares. So let's do that first. 2 squared is 4, 3 squared, 9, 4 squared, 16, 5 squared, 25, 6 squared, 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared is 144. Memorizing these perfect squares will help you, and of course you could even go further. Now, the largest perfect square that goes into 27 is 9. We know that 27 is 9 times 3, so we're going to rewrite this as the square root of 9 times the square root of 3. Now, it's important to leave the square roots on here, because the square root of 27 is equal to the square root of 9 times the square root of 3. So if we leave the square roots on here, then we can make sure we're going to take the square root of 9 to actually simplify this. We know the square root of 9 is 3, so we'll substitute 3 for square root of 9. And this square root of 3 we can't simplify, so we leave that, and this is our final answer. For our second example, let's do the square root of 20. Now you can go ahead and pause the video and solve this yourself if you're ready. The largest perfect square that goes into 20 is 4. The square root of 20 is equal to the square root of 4 times the square root of 5, because 4 times 5 is 20. The square root of 4 is 2, and we can't simplify the square root of 5, so we leave it as square root of 5, and that is our final answer. For our third example, let's do the square root of x squared. So now we're going to get into simplifying square roots with variables. I'm going to do several with variables, and then I'm going to combine numbers and variables. So technically, this is equal to the absolute value of x. A lot of the time, the absolute value bars do get left off, and it's just written as x. But let's just I'm going to show you why you really should write the absolute value of x. If x was negative 4, you see how I just substituted in negative 4 for that x. Well, we know the square root of negative 4 in parentheses squared is 4, because this is the square root of 16, which is 4. The square root always should come out to be a positive number. So if we just wrote x, x is technically negative 4, but again, a lot of the time it does just get left off. But for this video, I will be adding the absolute value bars. So let's just see why the square root of x squared is equal to x. So you can think about the square root and the square canceling each other out, since they are inverses of each other. Or you could even write it out as x times x. And whenever you're taking the square root, you're really looking for pairs of the same number multiplied together. Since you have a pair of x's here and the square root cancels out a pair, you are just left with x, or the absolute value of x. Let's look at the square root of x to the 4th next. So this is equal to x squared. We don't need absolute value bars around x squared, because anything squared is going to be a positive number. Now, you could write this out, and you can see that you have 2 pairs here, and so that's why you would take out an x and take out another x and multiply those together for your answer of x squared. Next, let's look at the square root of x cubed. So we have x times x times x. So we have one pair, so we're going to take out one x, and then we have this x left underneath the square root. Now again, technically we should have the absolute value bars around the 1x that we took out, and this is our final answer. Next, let's look at the square root of x to the 8th. Now, if we were to write all this out, we would have 8 x's, 1, 2, 3, 4, 5, 7, 8, and we would have 4 pairs. Now, hopefully, you are really seeing a pattern to this. So we're going to take out 1x, 2x's, 3x's, 4x's. So this is equal to x to the 4th. So what do you think the shortcut is? What we're going to do is we're going to take the highest even number that's inside here. So in this case, the highest even number would be 2. In this case, since 8 is even, it's 8. And we're going to divide this number by 2 to get this answer, since we're looking for pairs with a square root. So let's do this example. If we had x to the 50th, the square root of x to the 50th, then that would be x to the 25, because you would have 25 pairs. You just take 50 divided by 2. Let's just do one more of these. If we had x to the 51st power, okay, then the closest but lower even number is 50, so we could take out 25 x's, but we would be left with 1x under the square root. Now, since 25 is an odd number, an odd exponent, we really should have the absolute value bars around our x. And this is our final answer. Let's look at a bigger number. So let's do the square root of 180. Now again, it helps to have our list of perfect squares. I'm going to show you 2 ways to simplify the square root of 180. You may think, well, this is equal to 9 times 20, because 9 times 2 is 18. So you would do the square root of 9 times the square root of 20. And the square root of 9 is 3. However, there is still a perfect square inside of 20. We know that 20 is the square root of 4 times the square root of 5. And we know the square root of 4 is 2. And we can't simplify the square root of 5. And then we multiply these two numbers together. So our final simplified answer is 6 times the square root of 5. Now, this shows you that since this is 6, that there is a 30, we could have divided 180 into 36 times 5. And so you might have recognized instead that the square root of 180 could have been simplified to the square root of 36 times the square root of 5 and done it in one easy step and said, okay, that's 6 times the square root of 5. But you can just simplify it and just keep simplifying it till you're sure that there's no perfect squares left under the radical. Let's do one with a number and a variable. So again, you might think 72, okay, that's 9 times 8. Or you might look for a larger perfect square that goes in 72, so you can do it in one easy step. So this is equal to the square root of 36 times the square root of 2. And then we know that the square root of x squared is the absolute value of x. So we're going to take the square root of 36, that's 6. We're going to take the square root of x squared, that's the absolute value of x, and then we're going to leave our square root of 2. These are all multiplied together, and this is our final answer. It doesn't have to be in this order, but this is a standard order for these answers, that you would put your number first, then your variable, and then your square root. If you do end up putting one of these behind the radical, just make sure that you're very clear about what's under the radical and what's not. Let's do several more with numbers and variables. let's do the square root of 150, x to the 6th, and y to the 5th. So we can break this up into each piece. We can do the square root of 150, the square root of x to the 6th, and the square root of y to the 5th. So you could split it up if that makes it easier to look at. You don't have to do this. So what is the biggest perfect square that goes into 150? 25. 150 is 25 times 6. Now remember our trick for taking the square root of x to any even number. You're just going to divide this number by 2 because you're looking for pairs. So this is going to simplify to x to the 3rd. Now this is an odd exponent here, y to the 5th. And so we know that we could take out 2 pairs. So we'll have y squared, but then 1y will still be left under the square root. So now let's combine everything. We know the square root of 25 is 5, and then we'll put our variables that are outside the square roots, x cubed and y squared, and then we'll leave everything that's still under the square root of 6 and the square root of y. We'll put those together. Properties of radicals allow us to do that, and this is our final simplified answer. The next example will be the square root of 112 times x to the 11th times y to the 9th. I'm going to write this a little bit differently from the way that I wrote the last one, just so you can see a different style, and then you can decide what you like better. So what is the biggest perfect square that goes into 112? You know that 112 is an even number, so if you have a calculator, you could, just try to maybe divide it by 36 or 16 or 4 or 2. You can start off with dividing it by an even number, but really the shortest way is going to be looking for the biggest perfect square that's inside there. So you can see that 16 goes into 112 7 times. So we could rewrite this as the square root of 16 times the square root of 7. Now, our x to the 11th, we know that 10 is the closest even number that's lower, and so we know we're going to be able to take out 5 x's, but we're going to have 1 left under the square root. Same thing for 9. 8 is the next lowest even number, so we know we're going to be able to take out half of those, so that's 4. And we'll still be left with the square root of y. The square root of 16 is 4. And we'll just multiply everything that we have, and then we'll rewrite it so that we write everything that we took out of the square roots. And then we'll do the square root of everything we still have under the square root, so 7xy. And this is our final simplified answer. Let's look at one more type of this example, and then we'll move on to adding and subtracting and multiplying. So we're going to simplify the square root of 128, x to the 21st, y to the 10th. So you can take a calculator and divide 128 by several of these even perfect squares and see what the biggest perfect square is. So hopefully you found 64. This is 128 is 64 times 2. X to the 21st, you can take out x to the 10th, half of 20, and then you are still left with a square root of x. And y to the 10th, you'll be able to take out the 5 pairs. So the square root of 64 is 8. And then we will rewrite it writing everything that we took out of the square roots. And then we're left with the square root of 2 times x. And this is our final answer. Now we'll move on to adding, subtracting, and multiplying, which will still include simplifying as well. Now we'll move on to adding and subtracting radicals. The first 2 examples will be simple, and then the next examples will include simplifying along with the adding and subtracting. Now, as long as we have the same square root, the square root of 3 and the square root of 3 here, and make sure you're paying attention to adding or subtracting, then we can combine these numbers in the front. So this is going to equal 9 times the square root of 3. Because the square root of 3 is just a number. It's really just like if you had 5x plus 4x, then you would say that's 9x. Well, the variable x just stands for a number. Could be the square root of 3. So as long as you're multiplying 5 times some number plus 4 times some number, that would equal 9 times that same number. The same thing for when we are subtracting. 8 times the square root of 6 minus 10 times the square root of 6 will be negative 2 times the square root of 6. You're just combining that 8 and that negative 10 since they both have the square root of 6. Now let's look at negative square root of 20 minus 2 square root of 45. We cannot combine our negative 1 and our negative 2 since we don't have the same thing under the radical called a radicand. So we need to simplify first. We know that the square root of 20 can be simplified because there's a square root of 4 inside a square root of 20. And we know the square root of 45 can be simplified because we know there's a square root of 9 in there. So the square root of 4 is 2. So we have negative 2 times the square root of 5 minus, we know that the square root of 9 is 3. So we need to multiply this 2 and this 3. And now we can combine our negative 2 and our negative 6 because we have the same radical, square root of 5, on both. So this is going to equal negative 8 times the square root of 5. We cannot add these together yet because this has a square root of 2 and this has a square root of 8. So we'll simplify first. We can't simplify the square root of 2, but we can simplify the square root of 8. That's the square root of 4 times the square root of 2. We know that the square root of 4 is 2. So this is 6 times the square root of 2. Now that we have square root of 2 here, square root of 2 here, we can do negative 3 plus 6. So we have 3 times the square root of 2 is our final answer. Now we'll move on to multiplying radicals. The first couple of examples will be very simple, and then we will combine simplifying with multiplying. Just so we remember exactly what our properties are when we're multiplying radicals. The square root of 3 times the square root of 2 is the square root of 6. You multiply these numbers. If this is a square root and this is a square root, then we can multiply what's underneath. Just like when we are going backwards and simplifying how we'll break it up. It's just the exact same thing. Now, if you have the same radicand, like you're multiplying the square root of 3 times the square root of 3, then that is just 3. I would really skip the middle step of saying, well, this is the square root of 9, which is 3. You're just creating, not that that is wrong, but you're just creating more work for yourself. If you see that you have the exact same thing under your radical, then you have that thing squared. And so your square root and square will cancel. So you're always just left with whatever is under the radical if you have the same thing. This will help a lot when the numbers are bigger, and so you'll just create a lot less work for yourself. For our next example, let's do negative 2 times the square root of 12 times 3 times the square root of 3. Now you can see that you can simplify the square root of 12. So there are two ways to do this. Since these numbers aren't very big, you can just multiply your radicands, which you have underneath the square root, and then you can also just multiply your outside numbers. So I'm going to show you two ways to do this. The first way is to just multiply what's on the outside, so negative 2 times 3 is negative 6, and multiply your radicands. So 12 times 3 stays under the square root. 12 times 3 is 36. Since 36 is a perfect square, we have negative 6 times 6, which our final answer ends up being negative 36. The other way that we could have done it is to simplify the square root of 12 first. We know that the square root of 12 is the square root of 4 times the square root of 3. And since we're multiplying all these numbers, and the order in which we multiply does not matter, then we could do this negative 2 times 2, since the square root of 4 is 2, times 3, since those are all outside the radical now, and then the square root of 3 times square root of 3, which we know is just 3. So we'll multiply negative 2 times 2 is negative 4, times 3 is negative 12, times 3 is negative 36. So you can see that either way we get the exact same answer. For this next example, we have 4 times the square root of 15 times 3 times the square root of 5. Now instead of multiplying 15 and 5, I know that there is a 5 in 15, and that will just make it a lot easier for me to multiply and simplify instead of first multiplying 15 times 5 and then finding a perfect square of 25. So I'm going to change the square root of 15 times the square root of 5 times the square root of 3. And then I'm going to write this down, times 3 times the square root of 5. And I'm going to combine these outside numbers. This is 4 and this is 3. 4 times 3, that's 12. And I'm going to combine this square root of 5 times this square root of 5, which I know is just 5. And then I have this square root of 3 left. So I'm just going to write down my square root of 3. So now I need to multiply 12 times 5, which is 60, times the square root of 3, and that's my final answer. If you look at this next example, 8 times the square root of 18 times 5 times the square root of 27, you can see where this method comes in really handy. Instead of having to multiply 18 times 27 and then figuring out that 81 is the perfect square inside of that product, you really can just see, okay, I have a 9 in 18 and I have a 9 in 27, and just simplify it that way. And that way you don't need a calculator either. So we'll have this 8 times this 5 on the outside. We could go ahead and multiply those. The order in which you multiply really doesn't matter. So we'll take the square root of 18 and we'll split that up into the square root of 9 times the square root of 2. And we'll take our square root of 27 and we'll split that up into square root of 9 times square root of 3. So then we can see that we have square root of 9 times square root of 9, which we know is just 9. So we have 40 times 9 times, we have the square root of 2 times the square root of 3. So we will have to leave that as the square root of 6, since we cannot simplify 2 or 3. We'll multiply those radicands together. 40 times 9, we'll think about 4 times 9 is 36. So 40 times 9 is 360 times the square root of 6, and that is our final answer. For our last example, let's look at 2 times the square root of 42 times 5 times the square root of 54. Go ahead and pause the video and try this one on your own. So hopefully you saw that there's a 6 inside of 42 and a 6 inside of 54. So we could go ahead and multiply our 2 and our 5 that are on the outside. So we can go ahead and do that and say 10. And then we'll split the square root of 42 into the square root of 6 times the square root of 7. And we'll split 54 into the square root of 6 times the square root of 9. So then we have square root of 6 times square root of 6. So that's just 6. The square root of 7, we can't simplify, so we leave that as square root of 7. But the square root of 9 is 3, so we'll change that to 3. So then we need to multiply 10 times 6 times 3. So 10 times 6 is 60, times 3 is 180. And then we have our square root of 7 left. And that is our final answer. Please check out my other videos for adding, subtracting, and simplifying with cube roots. And please comment on this video and hit the like button and subscribe to my channel.